let's start this. Already so much thing I share with you guys. So Faraday's law, they in this particular class, the students who join late, three important things we are going to discuss: magnetic flux, Faraday's experiment, and then EMF or electromagnetic induction, the principle, or electromotive force. So the first thing, what is EMI? EMI are two kinds of thing. EMI like every month income something, you can say whenever EMI we need to pay, whenever we take a debt or loan, or this or in finance. So one EMI here we also have in science, which is electromagnetic induction. So what is that? The reverse or the reverse process of generation of electric current with the moving magnetic field. So is it possible for moving things to generate electric currents? Let's look at that. How can you tell whether there is a connection between electricity and magnetism? So it is going to be discussed. It is going to be said EMI. I mean EMI is the process where we're gonna discuss this thing. Electromagnetic induction. What is the meaning of this? We're going to find the electromotive force, or you can say basically in general, electromotive force is nothing but a kind of a potential difference. Okay, so electromagnetic induction, it's going to generate electromagnetic force. Just a minute. Wait. Why it's not working? I need to write again. So EMI stands for electromagnetic induction, which is going to generate electromagnetic force. Okay, and what it is we're going to discuss. Electromagnetic induction. What is this and what is the output of that? Electromagnetic force or electromotive force. Electromotive force is nothing but a kind of a force which this particular word itself is made up of two words. Electro means electron, motive means motion. Okay, a kind of a force which is going to generate, which is going to move your electron, or whenever a movement of electron is going to be observed, so we get electric current. Is this clear, everyone? Is this clear, na? Good. Okay, so what is the flux? In general, we are talking about right now, the flux is like we understood electric flux first of all, or you can say in general flux. So you guys know about the electric flux. So on the basis of that, on the analogy of that, we are going to understand flux in general. So basically flux is nothing for any particular area or for any particular area vector whenever the field lines, that field lines can be magnetic field lines, that field lines can be electric field lines, that field lines can be any other also. Okay, for example, you can say light field lines, or you can say intensity, or light ray is going to be. So flux is nothing, you can say, when field lines passing through the area where the area vector, we get flux. Okay, we get flux. So in general, we have two types of flux: electric flux phi E, that is electric field lines E dot area vector, and that is EA cos theta, and that is beta EA cos theta. Is this clear, everyone? In the same way, here on the left hand we have an electric flux, electric field is passing through this per unit area, and on the right hand side we have a magnetic flux. So same thing, phi B, magnetic field lines B dot A, and the same thing BA cos theta. Nothing is going to be changed because flux is a in general property of field lines whenever they passing through per unit area. Is this clear? In the same way, Good evening, sir. Sorry for late. I asked my mother to wear. Okay, it's okay, but it's okay. Okay, so the field lines in general can be two types. Right now, you can see there are so many other types also. You can understand on the basis of smoke field line also. What is the meaning of smoke? In general, smoke is a field. For example, you burn some wooden or woods. So in any particular periphery, you have seen this kind of effect. I'm not good at it. Okay, in this kind of smoke, a gray color or a white color. Clear? Now, if I draw this particular area, if I draw this particular area, and I draw this thing also, which is a vector. Clear? So the amount of smoke or the amount of smoke, you can say lines or imaginary smoke is going to be passes through this area is known as smoke flux. But in general, in physics, don't worry about smoke or fluid. We are going to discuss about electric flux only and magnetic flux. Is this clear, everyone? Clear, everyone, or not? Is this clear, na beta? Okay, in real life, what where we going to use this particular concept? Electric generator, electric motor, wireless charger. Like these important, I mean, these are the important concept. What is this? EMI. Okay, okay, let me write the name first. EMI, EMF, or you can say EMI, EMF, or what is that? A Lenz law or not eddy current, AC current. Okay, so basically electric generator, electric motor, or wireless chargers based on this particular principles what we're going to discuss. EMI, EMF, AC current by the help of this simple techniques and practices. Is this clear, everyone? Okay, good. Moving ahead, electromagnetic induction. So this is the proper definition, and let's what it is in general. So electromagnetic induction, what is this? The induction of a the induction of an electromotive force by the passage of a conductor through a magnetic field or by a change in magnetic flux in a magnetic field is known as electromagnetic induction. Oh my goodness, so much words. I mean, so much hard words. Okay, in general, what is the meaning of this? See, initially we see there is a charge in any particular matter in everything, right? So when the charge starts moving, there are one effect we understood initially. Initially means in 10th class. Whenever a charge starts moving, so it generates a electric current. Okay, fair enough, good enough. Then in the next chapter in 10th class also, we see the magnetic effect of electric current. Fair enough, good enough. Means whenever a charge is in the motion, so it generates a magnetic field or a magnetic force, QVB, if you remember. Okay. So charge is, when charge starts moving, this is the just reverse concept. When charge starts moving, so we have a electric current, or you can say current in general. It is continuously moving, so we have a electric current, and then its effect are the two important effects: heating effect, and another is magnetic effect. Two important effect is heating. I'm not going to write effect now, and the second one is magnetic. Is this clear, everyone? There are the two important effect of whenever a electron starts moving, and we have also magnetic force, which is QVB. Means what is the meaning of saying that? If I start moving this particular charge in any particular field which is related, or you can say which have a magnetic field in general, suppose here, so I get the magnetic field also, because I need three things at least. A moving charge means velocity in a charge, or a magnetic field. Is this clear, everyone? Magnetic field B here in the coming direction. So this thing we already know. Now in this particular chapter we are going to prove if we are going to reverse this thing. Means what is the meaning of reverse? If we start moving, if we start moving magnetic field, if we start moving magnetic field, can we get the current? Simple statement, no here and there talk. Okay, so that is the question. And yes, we get it. How we get it, how much amount we get it, what is the formula, what is the use, and everything we're going to discuss in the coming slide. Is this clear? So electromagnetic induction is nothing, just it is a process. Induction means induce, or you can say production without touching. That is the meaning of induction if you don't know. So there are two processes of charge transfer, conduction and induction. Conduction you need a you can say physical touch. In induction you don't need. So what is the meaning of saying that we're going to generate current with the process of induction without even touching this magnetic field with this coil? Simple thing, we try, we going to move this magnetic field towards this coil, and there is a production of current. In a vice versa, we're going to move this coil towards the magnetic field also. So then there is also, you can say, there is a production of current is going to be seen in the galvanometer. And instead of magnetic field, or you can say instead of magnet, if I put a electromagnetic, or you can say what is a electromagnet? Another coil which is having a current. So any particular coil having a current is going to generate a magnetic field. So the main things are two there, a magnetic field and a moving magnetic field. Simple. We don't need to find the cause of a magnetic field. We just need to find the moving magnetic field. Clear everyone? So the main thing here we're going to discuss, whatever I'm saying, these are the experiments in general basically. So what is electromagnetic induction? Means till now whatever we learned the concept, like whenever a charge starts moving, so it generates a electric current. Okay, fair enough, good enough. Whenever electric current is moving, so it gives us two effects, heating effect, or you can say magnetic effects. These are the basically effects. Okay, so heating effect we get, magnetic effect we get. So we are trying to find in a reverse way. Like if I move my magnetic field, so can I get the electric field, or you can say electric current in reverse also? So the answer is yes. Clear? But there is one necessary condition apply there. The magnetic field or the coil, one of them is in the motion. Simple. Clear? If I just, if this particular motion, you can say direction of motion, if this magnetic field at rest, so we don't get any particular deflection in the galvanometer. And what is the meaning of that? We don't get any particular current, as simple as that. And that is written in the small two lines. The induction of an electromotive force. Electromotive force means potential, or a electromotive force basically a potential. And when we have a potential, so we can get the current also. Force by the passage of conductor through a magnetic field, or by a change in magnetic flux, okay, in a magnetic field, is known as electromagnetic induction. So these are the experiments. So this is your simple experiment number 1. So whatever I am saying since last 5 minutes or 10 minutes at least, so that is the thing. As you can see, there is a magnetic field. Okay, so there is a magnet, or you can say permanent magnet, permanent magnet. So this permanent magnet gives us a magnetic field. So whenever we move this magnetic, whenever we move this magnetic field towards this coil, so you can see the generation of current, and there is the current, you can see. Okay, this is the current, as you can see in the arrow. Basically what happens, this particular galvanometer in needle is initially is there, and you get the deflection, and the deflection shows us the current, presence of current. Okay, deflection in galvanometer makes deflection in galvanometer proves the presence of either voltage, which is EMF, presence of EMF or current. Is this clear? Because with the help of galvanometer we can get two things. Either we can convert this galvanometer into the voltmeter, or either we can convert this galvanometer into the ammeter. Is this clear now? So that is the device, instrument, which can observe, which can get, which can gives us any of the thing. Clear? So that is your experiment number 1, important one. And it is very important for CBSE because they ask what is the EMI and write the 3 experiments of Faradays and prove, instead of saying right, prove that particular this thing, and some simple question related to the magnetic flux. The second experiment is, now as you can see, instead of permanent magnet, here I can switch my permanent magnet with temporary magnet. Temporary magnet. How it is a temporary magnet? Okay, as you can see, in this there is a anti-clockwise current. This is the anti-clockwise current, na? Clear? So whenever there is an anti-clockwise current, so what is the meaning of N? This is kind of, there is a north pole here. Okay, how you can get the magnetic field with the clockwise and anti-clockwise? Very simple, with the right hand rule. If there is a clockwise, what here? Okay, in this way my clock is going to be, right? So in this way my clock is going to be, so the magnetic field is downward, and anti-clockwise is going to be in this way, so magnetic field is going to be upward. So whenever there is a upward means north pole. And very basic thing I can teach you here as well. See, anti-clockwise, you can get from this also. This is clock or this is anti-clock. So I need to change the color. So as we can see, this is clockwise. Okay, so how it can move? In the shape of S. So there is a south pole. If it is a anti-clockwise, so this is anti-clockwise. How it can move? In the shape of N. Simple. So whenever in any particular loop, in any particular current carrying loop, there is an anti-clockwise current, so there is a north pole. Clear? Of a magnet. And whenever there is a north pole of a magnet, what does it state? If a north pole of a magnet, so obviously from here the magnetic field is going to be arise, and here we are going to get the, see, in this way. Is this clearly understood now? Because magnetic field is arises or generate from the north pole. It is going to end at the south pole. Beta, please turn on your cameras too. Is this clear, everyone? Yes, Dharmeshwar, Kyle Netra, Shrutika, other than Shrutika, Sai, Shrushita, everyone. So that is the thing. So this is a temporary magnet until unless I have this, which is a battery or a cell. Okay, until unless I have this battery, so there is a current, and whenever there is a current, so there is a temporary magnet. Again, when I start moving my this temporary magnet okay, towards this coil, so again I can see the deflection, again I can see the generation of current. So this is the proven thing. Is this clear, everyone? Is this clear now? Okay, in a same sense, now what if I don't want to move my magnetic field? It's okay, you can move your coil also. So the main thing is relative motion. What is the meaning of relative? There are two objects. If you don't want to move this, you can move this. Clear? The main thing is relative motion. Suppose it is my magnet. So either you can move your magnet, okay, suppose this fist of mine, this 4 fingers is you can say coil in this way. So either you can move the magnet, or either you can move the coil. One of the motion is relative. One thing is important here, and that thing we are going to see in the next slide. So here, experiment 3. What is the meaning of this experiment 3? Now, coil 1, coil 2. So in this particular thing, what we can see, this is your temporary magnet again, temporary magnet. Okay, so now we start moving this coil towards this. So obviously there is a magnetic field. Okay, there is a magnetic field. There is a magnetic field. There is a magnetic field in this way. Suppose, what is the meaning of saying? I mean, this is the north. So the moment I start moving my this particular coil into this region, so again I can see the current. So you can write as a note, what is the note here? For EMI, or you can say to get to get current, no, for EMI, electromagnetic induction, for EMI phenomenon, the relative motion, or the relative motion in between the magnetic field and coil is necessary. That is the note. Is this clear, beta, everyone? Is this clear or understood? Okay. So these are the basic 3 experiments, or you can write it down or laws also, but these are the basic experiments of Faraday. And they ask directly this. Okay, how many of you know how to draw this curly bracket? Are you able to draw this much clear? See, I practice so many times. That's how I get this. I mean, tomorrow I see a meme. There's an art page. I mean, they draw so much beautiful things, but they can't able to draw this. But there is one thing also, I can also able to draw this only on the left hand side. See, I can draw, I mean, I can, array beta, that is keyboard. Don't worry, I give you the access sometimes with the pen also. Then you try. See, I cannot able to draw that much perfect on the right hand side. But for left hand side, I don't know what happened. It is going to be perfect. See, okay. So that there is a note, and we done with the experiments. Now there is a table is going to be, and whatever we discussed till now, that is you going to get in a tabular form. Okay, important enough. So what is experiment? What is observation? So first one is, let's take this color. Experiment number 1. Place a magnet near a conducting loop with a galvanometer in the circuit. No current flow through the galvanometer. Why so? Tell me why. A moment ago I give you the reason. Tell me why it is no, I mean the galvanometer shows no current. Tell me anyone please. See? Tell me. I mean you can speak up also. Why there is no current flow? You tell me, beta Sai, are you there? In the first line, why it is written there is no current flow through the galvanometer? Everything is perfect here. What happens? In a minute, not even a minute, few seconds ago, I tell you guys, I stated this so many times. Relative motion is not done. Yes, beta, exactly. Don't sleep at least. You look like you are not sleeping since last 3 days. How much days you are not sleeping properly? Tell me. Sai, I'm talking to you right now. It is not equal. What not equal, beta? The main thing is relative motion. I tell you guys here, for EMI, electromagnetic induction phenomenon, I don't know what I write this, Phenomenon. That is phenomenon. Okay. For the EMI phenomenon, the relative motion in between the magnetic field and the coil is necessary. So that is the thing. No current flows through because you can see directly there is no arrow on this particular magnet, not on this. So arrow shows the motion. Is this clear now? So any one of the thing is need to be in motion, either the coil, either the magnetic field. Clear? Clear, sir? Focus a little bit. Okay, so there is no current flows through. In the second line, move the magnet towards the loop. The galvanometer register a current. Obviously, it is going to, because now what is saying, move the magnet towards the loop. So this magnet is moving towards the loop, or reverse the direction of a motion. The galvanometer deflection is going to be reversed. Okay, is this clear, everyone? Because we see that AC have a direction that is going to be flow in this way, sinusoidal. You're going to see in a minute also. So the moment we change the direction of a motion of this particular thing means either the motion of magnetic field of a due to the magnet, or the motion of a the relative motion due in the coil. So the moment we get this thing, the deflection of the galvanometer we are going to see. Is this clear? So that is why it is important. Again, I am stating this: motion or relative motion in between magnetic field and the coil is going to be important. Experiment observation second: reverse the polarity of the magnet and move the magnet towards the loop. The galvanometer deflection going to be reversed. Okay. Keep the magnet fixed and move the coil towards the magnet. The galvanometer register current also. So in all the cases, in each particular cases, it is going to be here instead of this. Okay, just a minute. I need to erase this. I need to redraw this. There is a galvanometer, or in this galvanometer, I can see the deflection in this way, because it is going to be reversed from the previous page. What is the meaning of saying that? If I reverse the polarity of this particular thing, okay, then I need to change this also. If I am going to reverse the polarity of this, one side is S now and another side is N. I cannot draw small n. Yeah. Okay. So N S. Here you can see N near to the coil and S farther. Here I change the polarity, reverse the polarity. So your deflection in the galvanometer is going to be reversed or reflected. Is this clear? But the main thing is again the motion. Here also the necessary thing is this motion. Here you can see the arrow on this particular coil. If there is no arrow, means there is no motion. I write it down also. Arrow here represents motion. Represent the motion of a magnet or a coil. Is this clear, everyone? Okay, so that is the meaning. Okay, moving ahead. Experiments, observation. This is the experiments and this is the observation. Now magnitude wise you going to get also. What is the meaning of saying that? Back to this page. What if I there is a two magnets, suppose. Okay, there are two magnets, north south. This is north, this is south. Okay, so if I move this particular magnet, if I move this particular magnet with, you can say, not this color, this, with velocity you can say 10 meter per second, and I am moving this, and you can say there is a relative motion for this magnet is going to be V equals to 2 meter per second. So So obviously, whenever this particular movement is going to be magnet 1, okay. So in the motion, in the relative motion of magnetic field or magnet 1, I get the more amount of current because of large relative motion there. Clear everyone? Means the faster you move, the more amount of electric current or induced EMF you're going to get. Is this clear, beta? Everyone? Parikshit, Susita, Sai, Srutika, Trivikram, Kaila, and Vishwanath also. Clear? So that the thing, I mean this particular things is going to be written on the table. And obviously, if it is going to be change the direction, means instead of movement this, instead of this particular movement, I move this particular magnet in this direction, in reverse direction. So two things going to be happen there. The polarity is going to change first of all. This deflection you can see in this side. And the second thing, it is very minute. What is the meaning of minute? Very small. Because the velocity is less as compared to the upper magnet, or as compared to the magnet 1. And the direction is also changed. So these things is going to be written there. Akash, Kanan, beta, are you there? You are not visible in this feed. Where are you? And how are you? Because you, you were so irregular. Okay. So these are the things written over there. Increase the speed of the magnet, the deflection increases. Deflection means current basically. Or EMF also maybe. Okay, I am writing two of the things. EMF or current. Or current I am going to represent with IAC. Okay. Increase the strength of the magnet, again the deflection is increases. Why so? Because here magnetic field is increases. So again the same thing, EMF and IAC. Increase the diameter of the coil, the deflection increases. Why so? Because obviously there is a, this particular current is going to be generate more because radius is more. Okay, you are going to confuse why everything is going to be because this everything is related with this, which is phi b. Phi b is magnetic field and area, and not this only relative motion of this. So what is the relative motion of this? D phi by dt. Okay, right now this thing. Okay, means we know there is a magnetic field, so there is an area also. So if the area, if the loop radius is going to increase, so in general more magnetic flux is going to pass through this particular loop. So more magnetic flux is going to pass. So obviously more amount of EMF or EMI phenomenon is going to get. More velocity, or you can say less time, more current or more EMF in a simple state. Sir, I'm attending class regularly now. Good. Okay. Fix the speed of magnet, but repeat the experiment with the magnet closer to the coil. Obviously, the deflection is increases. Closer to the coil means near to the coil. So again, this near stating that current is going to pass through the coil. Move the coil, move the magnet at an angle to the plane of the coil. Deflection decreases. What is the meaning of this? Someone please tell me. Angle to the plane. What is the meaning of angle to the plane? Anyone please? And why it is say deflection is zero? Very simple thing you can understand from this even one word. Tell me anyone. Move it to slides of coil. Okay. Cross two line. Okay. But I am not asking plane. This I am asking at an angle to the plane. What is this meaning? What is the meaning of this? And this particular thing gives you some idea or a hint. Anyone? Where is girl power today? Susita, Sai, Sutika, Kyle Netra. Why are you not saying anything? You don't understand anything. Cross two lines gives us plane, not angle to the plane. See, there is very basic thing. The angle is going to be 90 degrees. Yeah, intersecting point of two lines. No, beta, intersecting point of two lines is zero, origin. I, is this serious thing? I need to teach you plane also then. See, if perpendicular exactly 90 degree angle, I already stated that. The moment I write this magnetic flux and this deflection is zero, so automatically you get this phi b is equals to b a cos theta. Okay, and this theta is angle to the plane, and this theta angle to the plane means deflection is zero, means phi b is not zero because of b or a or movement, it is because of zero due to this theta. So when this theta zero, so cos theta 0 means cos 90 degree. Simple. Theta equals to 90 degree. That is the meaning of stating this at an angle to the plane. And more precisely, this is your plane, right? And how it is a plane? Someone asked me, so I can draw this also. This is my one axis, this is my another axis, so I can consider it is a plane. Clear? And for this particular plane, this is my angle of a area vector. And what is the this move the magnet at an angle to the plane? This is my plane, na? This is my plane and this area. So if I move my magnet, first of all I draw a magnet. If I move my magnet into this region or into this angle, so what is happening here? The angle between magnetic field, right? If you moving your magnet, sir, at what condition will deflection decreases? It is kept an angle. Ha beta, that is I am stating here. Wait for a while. That is, this is your area vector direction, right? Area vector, or you can say normal to the area vector, and that is your magnetic field. So here you can see the angle between these two is 90 degrees. Okay. Did you get your answer? This particular condition is minimum 0. Or the condition where we're going to decrease, either we decrease the area of a coil, like see, when I increase this thing, simple stating phenomenon, when I increase the magnet or speed of a magnet, so EMF or deflection is increased. So if I decrease the speed, it is going to decrease also. If I decrease the strength of a magnet, it is decrease also. If I decrease the diameter of a coil, it is decrease also. Clear? So these are the condition of a decreasing. When we get 0, and what is that particular condition? Even we are not decreasing anything, but we get the 0 deflection. Means 0 EMF or alternating current. So this particular condition. Is this clear, everyone? And whenever it is written over there, at an angle to the plane of the coil, or at an angle to the plane of the area, at an angle to the plane of this particular surface, meaning of this, theta is 90 degrees. Clear, everyone? Because in many, in physics, many times you are going to see this line, sentence, word. Clear? Is this clear, Kyle? I am talking to you now. You are visible to me. Is this clear, na? Good. Anyone have any doubt till now? Because I don't want to, you can see, give you a blooper. Suspicion, surprise. Yeah. I don't want to reveal the surprise just saying the one single formula. There is one single formula, EMF E minus d phi by dt. That is the formula. Simple. Okay. Even I say this, but I don't want to write even. So increase the number of turns of the coil, magnitude of current is going to be increased. Very simple, because it is how much number of coils is there. So the more amount of number of coil, more amount of EMF or more amount of IAC. current in general. Here we write directly current. See, before this there is a deflection written. Here the word current is going to be introduced. So current here basically is alternating current. Okay. So deflection decreases. Deflection is maximum when the magnet moves perpendicular. What is? Wait. Here deflection is maximum when perpendicular to the plane of coil. Should I teach this in something reverse? Magnetic field perpendicular to the plane. Okay, got it. So when magnetic field is moving perpendicular to the plane, means in this way, this is your plane, and if I instead of this is going to be parallel. If I move this magnet in this way, so that becomes parallel with area vector, and if I move this, so that becomes this particular thing perpendicular to the area, parallel to the area vector. Okay. Here the words is going to be very crucial. Deflection. Okay. Focus here. Deflection is maximum. What is the meaning of deflection? Phi B is needed to be maximum. That is B A cos theta. And this theta here, angle between B, which is a magnetic field, and area vector. Area vector is this. This is my area vector, normal to the plane. Okay. So deflection is maximum when magnet moves perpendicular to the plane. Perpendicular to the plane means this is your plane, and if it is moving perpendicular to the plane, so what happens then? This is your magnetic field and this is your area vector. Both of the things. This is your magnetic field now, and this is your area vector. So both the things are parallel, and when both the things are parallel, so theta is 0 degree, and when theta is 0 degree, phi B is going to be maximum. And what is maximum here? BA directly. Is this clear? This line is clear or not? Because this line confuses you so many times. Tell me everyone. See, perpendicular to the plane means parallel to the area vector. Either you can understand in this way, either you can understand in this way, according to the diagram. Tell me. See, this is my plane. Understand in this way. So area vector is there. Now if I move my magnet, okay. Suppose, wait. Suppose this is a plane, okay. This is the area vector, and my finger is going to be magnetic field. So when my finger is going to be perpendicular to this, in this way you can understand. Perpendicular to plane. This is my plane. So perpendicular to the plane, so the area vector and magnetic field direction is parallel. And when it is going to parallel to the, okay, this is, I need to hold this. Wait. Yeah. Okay. This is my area vector. This is the plane. Now if I move my magnet into in this direction, parallel to this, so what happens? Area vector and magnetic field direction are going to be perpendicular. So that is why this written, because this single line can confuse you, even sometimes me also. Is this clear, everyone? Or should I explain this again? Tell me, beta. Darshan, Sai, Parikshit, Kayal, Shushita, Dharmeshwaram, Vishwanath, everyone. Okay, in simple way again, because this diagram is okay. I remove this diagram and then I give you a proper, because that is clumsy. Clumsy means so many things. I write it down here. Just a minute. Okay. With this color we can draw the axis. This is my vertical axis. This is my this. Okay. With this color I can draw a plane. This is my plane. Sorry. this is my area vector. Now you can understand this rectangle is a plane, or this is your area vector. Now suppose this is your magnetic, or there is a magnet. I can move this magnet in a two way. This is your north pole, this is your south pole. There is a north pole, there is a south pole. Or I can draw my magnet in this way also. Okay. Now you can understand better way. This is north pole, this is south pole. So according to the plane, this is my plane, this where I write P. This is a plane. Yeah. For this plane, there are two kinds of movement going to be. First, parallel to the plane. Understand very clearly. Parallel to the plane, as you can see directly, is perpendicular to the normal vector, or is perpendicular to the area vector, because this one is direction of area vector. Direction of area, or you can say area vector. Direction of area vector. Clear? So when you move your magnetic field or a magnet parallel to the plane, because it is a plane and this is going to be parallel, so there the theta is going to be 90 degree. When we start moving this particular magnet perpendicular to the plane, okay, this is perpendicular to the plane, so it is parallel to the area vector, and that is why in perpendicular you get maximum. Okay, in perpendicular case we get maximum deflection, or in parallel case we get minimum. Is this clear everyone now? Is this clear everyone? I hope and I believe now it is this is going to be clear. Clear? Good. If you have any particular doubt still, you can rewatch this then. Okay, so there is a one simple question you need to find. Magnetic flux here. Everything is in front of you. Consider the following figure. A uniform magnetic field this much is directed along positive axis. So obviously the magnetic field direction is positive axis. What is the magnetic flux through the top surface? Now this is your top surface, if I'm not wrong. Okay, this is back, this is from, so obviously this is top. This one, I draw for you guys, even I don't want to. This one is your top surface. Is this clear everyone? And you can get the area also, because there is x, y, z, everything. Sir, if flux is 0, then deflection will be maximum. No, beta. I told you, flux is dependent on the, deflection is dependent on the flux. How it is going to be? If flux is 0, means neither magnetic field is going there or neither area. Flux is in general property which is needed to pass through within the coil, or either the coil pass through the flux. So if even in case flux is 0, deflection is 0. That's what I teach you here. Deflection is 0 when the magnet moves parallel to the plane. Parallel to the plane, you can say perpendicular to the area vector, means 0. Okay, for this you can understand phi b is dA cos theta. Okay, this is for perpendicular motion. That is how I write perpendicular. V in a physics, perpendicular motion. Okay, and that is how we write parallel, for parallel motion. For parallel motion, theta here is going to be 90 degree. And it is not Q, it is theta. So phi b is 0. Clear? And when phi b is 0, deflection is 0. Find this. Anyone? What is the correct answer? See, we have so many things to discuss, so please do this quickly. What is the answer of this? Anyone? If you guys are able to do that. See, that is directly picking from any particular JEE mains exam. Maybe 2014, 15 or 17, 18. B. Why put a question mark? Hate question mark in answer. If how B beta? Okay, this M is milli, first of all, small m. You understand, na? This small m is milli. Milli means 10 to the power minus 3. I expect a better thing, but it's okay. The answer is C. I don't need to explain you guys. See, the area, this is 30. So, this angle with this magnetic flux, or you can say with this, it is going to be 60 degree. So, that is why, and for 60 degree, this 10, this 10. And the top area is 10 into 10. Okay. So, with x-axis, it makes 60 degree. And because we have only magnetic flux in the x-axis, so 0.2 magnetic field, area, and cos theta. Cos 60 degrees half, if I'm not wrong. So 10 to the power minus 3 Weber, 1 milliweber. 1 milliweber. Answer is correct. Is this clear, everyone? Is this clear? Good. This one. Let me check. A coil has this much turns, this much area. It's the plane of the coil is placed at a right angle to the magnetic field. Induction of this. The coil is rotated through 180 degree. The average EMF induced. Okay, I don't teach you the EMF till now, so I can solve for you this. EMF is this one. NBA cos theta 2 minus cos theta 1. Okay, what the EMF and everything we discussing since last 1 hour. EMF is generally the electromagnetic force. Okay. EMF. You're going to get so many symbols, but the most appropriate is this one. Minus d phi by dt. And that is why relative motion and phi is magnetic flux. That is the formula. Is this clear, everyone? Now you get okay, what is the meaning of this? Should I draw that? If I able to? Yes, I can. Suppose these are my coils. Okay, not properly made. Suppose. And with this coil, I attach a galvanometer. With this coil, I attach a galvanometer. There is your galvanometer. Okay. Suppose. And there is a magnet now. So when this particular magnet is going to move, again there is NS. Okay. So there is a magnetic flux because of this coil, because of this area of coil. So here we have so many things, N, number of coils, or you can say number of turns in a coil. Phi, directly I am writing magnetic flux B dot A. So two things are there, clear? And the important thing, when you get this deflection, when there is a motion, or you can say relative motion. So rewriting everything simply. The electromagnetic force. What is the electromagnetic force? A force to move this deflection, or a force to move this needle, or you can say EMF in general. Because what we get here, either EMF, either voltage, or either current. So when we get a current, we get EMF here, electromotive force. That is nothing minus d phi by dt. Why this negative sign is going to be appear, we are going to discuss in a Lenz law. There is a law which is Lenz law, so we are going to discuss this. I don't wanna use this. Okay. So this is the surprise. I mean, this is the thing what I don't want to reveal, but it's okay. So this is your formula E minus NBA, which is cos theta 2 minus cos theta 1 divided by T, and here you can get the answer. Okay. Okay, let's take a break. Magnetic flux we already talked about a lot. You can read this, and there is a 5 to 10 minutes break. After a break, we're going to discuss its property and so, and then the important thing, EMF and the formula related to this. As I already stated, the half of the thing we already done in this. Whatever the major understanding part, whatever the major understanding. Now we're going to revise and repeat. Is this clear, everyone? Or you can see this also, or this also, but stick to this. This or maybe this. Hello, hello, hello. Am I audible? Am I visible, beta? Hello, hello, hello. Hello, 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 hello. In this class, Yajra is absent, Harima is absent, Jyotna is absent. So many students are absent. Is there any, particular time zone or period in which you have some examination and so? Specifically, the people who are living in South. I hope and believe maximum of you guys are from South, right? Turn on your cameras, everyone, please. Okay, so let's quickly do this. because the maximum thing and the major important thing we done. So what is a magnetic flux? Are you there? Just turn on your cameras, beta. Good. Be like Dharmeshwaram. Yeah. Open yourself because I can do that also. Yeah, so magnetic flux. The magnetic flux across a surface is defined as the surface integral of the normal component of a magnetic field B traveling through the surface. In electromagnetism, a branch of physics, it is indicated by letter phi or phi B. The Maxwell unit is the CGS unit, while the Weber unit is SI unit. Simple. Phi B equals to B dot A, here we skip the vector B A cos. Clear everyone? Actually, this is quite quarterly examination season, sir. Okay, beta. Quarterly. How many exams you are given? Quarterly. Seriously? I mean quarterly, then half yearly, then 3 by 4th, and then first. I mean final. In this way, you are. Oh my goodness. So many exams. God help you. Okay, so the magnetic flux. Already we know the physical terminology, physical phenomenon thing. Like if there is any particular area. Okay. If suppose there is an area. In this particular area, how much number of lines passing through in this way or any particular way with some angles, that particular thing is in general is the magnetic flux. As simple as that. Okay, so this is my magnetic field B, or this is my area vector A. So this is phi B, magnetic flux B dot A, B A cos theta. Now what is the magnetic flux? Phi B, B1 dot A1, B2 dot dA2, B3. I mean the surface integral or the summation of all. So this is magnetic flux passing through unit area. You don't get this kind of question at any time, so don't worry about it. Simple one thing, there is an area in this circular form, you can see that. Okay, there is a circular plate or an area and this particular magnetic field, and this is your area vector, this is the theta between them. Nothing more than that. Okay, understanding the magnetic flux for an infinitesimal. What does it mean? Very, very small area. dA is given by d phi. You can make a formula of this. Write this. So this is your formula number 1. Very simple, very basic. What is the meaning? For this particular small area. For this particular small area, there is a magnetic flux. I mean the magnetic field line passing through this particular small area is the magnetic flux. Nothing more than that. Understanding, okay, the magnetic flux for a surface is proportional to the number of field lines. Okay, this one is new. I mean how much number of field lines is passing through any particular unit area or particular area is gives you magnetic flux. Magnetic flux d phi for an area element dA is d phi v dot dA. Clear everyone? See, you understanding this thing now? Even if I'm scrolling the slides in this way, because the simple one stating line, how much number of lines passing through per unit area is magnetic flux. If I choose my area very small, so the magnetic flux is going to be very small. If I choose my area very large, so the magnetic flux is going to be very large. As simple as that. Clear everyone? Just type yes if it is clear, beta everyone. If you have any question, queries, you can ask. And beta please, because I don't want to say again and again and again and again. Good. Okay. So this is something new. What you going to see? So if the magnetic field B makes an angle theta with the normal to the surface, as shown in the figure, the normal component of the field B is B cos theta. Normal component of the field is this particular component. Okay, B cos theta. And in this case, the magnetic flux is given by phi B A cos theta or phi B dot A. The magnetic flux for a general surface is obtained by integrating, summing, means how much number of lines is passing through, summing the contribution of d phi as the area element dA ranges over any particular range. So phi equals to BA cos theta, phi max, as you can see whenever it is perpendicular or in the parallel to the area vector, and phi min in this way, or here instead of something is going to be 0. Is this clear, everyone? The same thing what we already done in the previous pages, that is with the help of diagram we can see here. Is this clear? Darshan, Sai, Dameshwaram or Kyle? Yeah, I'm asking to you guys. Is this clear, beta? Are you there or not? Be focused at least. See, who is understanding, who is not, I know this thing already. So if I'm asking to you guys, please respond at least. Is this clear? Everyone, is this clear? Should I move ahead? Good. Okay. So positive and negative flux, simple. If the theta is going to be less than this particular 90 degrees, so cos theta is going to be positive, and we get this particular thing which is a flux, a positive thing. So in case of a body present in a field, either uniform or non-uniform magnetic field, okay, outward flux is taken to the positive while inward flux is taken to the negative. What is the meaning of saying that? Good thing. Suppose this is your area. Okay, in this particular area, this is a ring in general. In this particular ring, area of this is something is going to be clear. So if I move my magnet in this way, so the flux, beta flux is going to be outward. Outward means, suppose this is okay. I cannot. Suppose this in this particular plane there is a ring, or in this ring this particular my magnetic field is going to be upward. So obviously outward, or if it is a plane of paper, my palm is a plane of paper and magnetic field or magnet is going in this way. So you can see that simply your magnetic flux is going to be positive. In a same case, if I reverse the direction of a motion of magnet, okay, in this way, not this color, yeah, this particular sense. So due to this magnet 1, due to magnet 1 and due to magnet 2, so phi 1 is positive, okay, and this phi 2 is negative, or you can say inward, and it is outward. And that is very easy. I mean, from where we get this positive negative analogy? From the axis, nothing more than that. These are my axes. Okay, so in this particular axis system, this is positive upward, this is negative. For y axis I'm talking right now, and right hand side x axis, okay, x, y prime, uh, x, x prime, and it is taken as a negative. Is this clear? So from the same analogy we took this. If the normal drawn on the surface is in the direction of the field, then the flux is taken as a positive. Again, here is my normal. I can take this color now. This is my normal vector. So if I move my magnet into the direction of a normal vector, so in this case theta is 0, as you can see there. Theta is 0. So when theta is 0 or less than 90 degree, if I move my magnet in this way a little bit, suppose now instead of simple 0, I can move my magnet in this way. I can do that now. It's my choice. It's in my hand. Wait. in this way I can do that also. So now I have some angle, or you can say this particular theta, not this, this particular theta is less than 90 degree. Clear now everyone? Clear? So when theta is 0 either, because it is moving in the direction same, or it is 90 degrees. So the flux taken as a positive. And if the normal to the surface is opposite to the direction of magnetic field, as you can see, normal is here. Okay, this is your normal. Okay, and normal is opposite to the direction of magnetic field. This is your magnetic field. Whenever I draw the arrow means here magnetic field direction, north there. So then the flux is taken as negative, as simple as that. And this is the meaning. Total flux for non-uniform field is going to be 0. Okay, because one side is going to be positive, another side is going to be negative. So for non-uniform field, the total flux is going to be 0. And for uniform field, the total flux is going to be 0 whenever there is a perpendicular case, whenever the theta is perpendicular. As you can see, this phi, which is a magnetic flux, is going to be 0 because it is perpendicular to the normal. This is your magnetic field. Na? Is this clear, everyone? This is very easy. Obviously, if you understand. If you try to learn, that is not going to be easy. Believe me. Never ever anything is going to be easy, specifically in physics, if you try to learn this. So for non-uniform field, how so? Very easy, because it is a circle, or you can say a loop or of a current, not current, a loop of a wire or any particular area which is in the circular form. So as you can see, for non-uniform thing, magnetic field is going in and going out, so total flux is 0. What we already discussed in the Gauss law of magnetism. For uniform thing, it is going to be 0 only and only pi b when b a cos theta, when theta is going to be 19 degrees. If b is not 0, obviously for uniform b is not 0, or a is not 0 also. Okay. So in this particular case, beta, what is going to be? Flux is 0 only and only when this is going to be. Flux is not 0 for this particular, neither for this. As you can see, total flux is 0. Why so? Because for this, it is going to be minus pi r square b, and that is positive pi r square b. And for this range even, for this region even, also your flux is 0. Okay. So in this scenario, the total flux for uniform, for non-uniform, it is going to be 0. Clear, everyone? Should I move ahead? Clear, beta na? Good. So magnetic flux density is per unit flux, or you can say magnetic flux per unit area. So magnetic flux density is B. Lines of force, lines of force are imaginary, but as magnetic flux associated with element area dA in magnetic field B, so flux is a real scalar physical quantity. Dimensions are ml2 t minus 2 a to the power minus 1. That is important. Sometimes you need to give this answer directly, and that is the simple 11th class concept. Magnetic field is going to be give you this because it is a force, and that per unit area. I mean, okay, how many of you know this MLT and dimensional formula for any particular thing? As we know, force is a dimension is M. Yes, beta, ask. ML T minus 2. That is the dimension of a force. Force is what? Okay, I know. Dimensional formula. Okay. Right. MA. Kilogram meter per second square. Okay. So from there, for magnetic flux, as we know, B dot A, and B is F equals to IBL sine theta. So from here you can get the dimension of this FIL. Okay. If it is L, okay, area is there also. Yeah. So using this particular terminology, we can get this phi. Important. I don't know for everything, sir, but for some, yeah, it's okay. So that's why in this way we can teach. Okay, phi is B dot A is area. Simple. How you can guide the dimension of this? Force divided by IL. I have separate dimension formula. Current in general. Current, sometimes in any particular book, you can see this way or this way. A is ampere here, not area. I is current. Okay. So there are few books in which you directly see I as a what? As a dimensional symbol. MLT, M stands for mass, L stands for length, T stands for time. Clear everyone? So that is important. Is this clear? Or do you have any doubt or question, query, anything, anyone? Sai, Susita, Kayal, Shakti. No. Clear na everyone? Okay. So magnetic flux unit is volt into second, SI unit. It is known as Weber or Tesla into meter per square. Why so? See, flux is simple. Let's say flux is not simple, sir. B A cos theta. Take this. B is can be Weber or 1 Weber is 1 volt into second in series system, or you can say that is going to be Tesla into meter. I mean this phi have a unit Weber Weber per meter square, sorry, Weber into meter square, and this is also Tesla into meter square. If your magnetic field is in the form of Tesla, so you can write this, and if it is in this form, so you can write this. Okay, directly Weber, because Weber is Tesla per meter square. So many. Okay, or Tesla is Weber per meter square. You can check it out. Tesla is Weber per meter square. These are the just symbols. I mean, even I am going to confuse sometimes. 1 Tesla is 1 Weber per meter square, means magnetic field per unit area. That is the meaning. That is the thing. Okay. So SI unit is volt into second sometimes, or this one Weber directly, or Tesla into meter square. So these are different things, different units. Nothing more than that. The major thing is CGS or Maxwell, sometimes MX. So 1 Weber equals to 1 volt into second, 10 to the power 8 EMU of proton into second, 10 to the power 8 Maxwell. This one is important. Okay. Maybe you are lucky enough to get this. 1 volt is 10 to the power EMU of potential. Electromagnetic unit, or ML2 T minus 2 corresponding to energy. So SI unit of magnetic flux will be joule per ampere, or you can say ampere is coulomb per second. So joule into second per coulomb. So that is how, as ampere is coulomb per second, so that is how you can get voltage into second. If someone is trying to, if someone is confused how we get Weber, is this way. So flux, which is a Weber, which is having unit ML2, and then T minus 2, A inverse, right? So this have a dimension of energy, and putting the dimension of energy joule per second. So joule into second is volt. Sorry, joule per coulomb is volt, and second is second. So that is how you can get this. Is this clear, everyone? With the dimensional formula, we can get this unit. Nothing more than that. Anyone have doubt or so? How it is energy? What is energy? Work done, potential energy, or even simple kinetic energy. Each particular energy is having the same dimension. So KE half mv square ml2 t minus 2, because V is LT minus 1. Na? Is this clear, everyone? Is this clear? So that is how you can correlate everything. Okay. I mean, this particular page you understand more when you revise the concept of dimension and units. So there is a one question. Do that. Very simple. At a given place, horizontal and vertical component of Earth's magnetic field BH and BV, we done in the previous chapter, along X and Y axis, respectively in the figure is not given. Okay. What is the total flux of Earth's magnetic field associated with area? Okay, if there is a, let me check this particular. A, B, C. Oh, they ask in this way. So I need to teach you this because obviously the area. So these are the diagrams. Just a minute. Obviously this is on the next slides. Okay. So as we know, in the horizontal component we have a Earth magnetic field BH, as we can see here. Okay, and in the vertical component BV. So for this area, this is your XY plane, this is your YZ plane, and this is your XZ plane. Quite clear, everyone, or not? First of all, tell me this. How you can find a plane in between two axes? That is easy, na? XY plane, Y so because it is in between X or Y axis. YZ, Y so because in between it is made up of Y or Z axis. Y so XZ plane because it is made up of X or Z axis. Simple. Nothing more. Okay. So they want the answers of this. So let's discuss. I mean, do that. Because B equals to IBH minus JBV is a constant, and phi equals to B dot DA, or you can say B dot A, where B is a constant. So everything is going to be dependent on area. Is this clear? So for area in XY plane, area is A into K. What is the meaning of this? Okay, again, as you can see, for XY plane, the area vector is in the direction of K. For YZ plane, it is in the direction of X. And for XZ plane, it is in the direction of, tell me, it is in the direction of what? I, J, K, X, Y, Z. In which direction it is? Just after seeing the diagram, tell me. In which direction, beta? K. Seriously? If it is already the area or a plane included X, Z, included Z, so how it is going to be in the K? A. What is A? What is A here? Wait. I mean, beta. Sorry. What is A here? Okay, understand again. Wait. Now here, try to understand. Maybe you see. This is your XY plane, right? Everyone clear? So for beta XY plane, this is your area vector arrow clearly mentioned. Which diagram? Good. In which diagram XZ plane is there? Now you tell me, Parikshit. Third, first, or second? In which diagram I have XZ plane? First one. Oh my goodness. Where first one? From right hand side or left hand side? Third, beta, third. Oh my god. It's okay. See, this is your first, this is your second, this is your third. XY plane, YZ plane, ZX plane. Now understood everyone? Okay. In XY plane, this arrow, in which direction it is? Obviously Z direction. This is in the Z direction, na? So for XY plane, my area vector is in the K direction. Okay, let me make first for each. For YZ plane, my area vector is in X direction. Understand in this way, for any particular plane, the axis made that particular plane, it is not going to be the area vector direction, as simple as that. And it is Y direction. Understood everyone? So when this YZ plane, so obviously the area vector here is in X direction, I direction. Here area vector is in K direction. Here area vector is in J direction, or you can say Y, X, or K, I write it down. So Z. Is this clear now? Understood now? Because I mean, without this, you are not going to understand what is written on the next page. Clear? So YZ plane, XY plane, I mean, how much it is the flux in XY, how much it is in YZ, how much it is in ZX. Do that. So B is this much, IBH or JBY, or you can write it this thing also in this way, but it is a constant quantity. BX, instead of X, we have H. Why negative? Because you can see it is towards the negative axis. That is why negative. Okay, for XY plane, area is AK. So phi XY H into J. It is going to be 0. Why so? Because I dot K and J dot K is 0. For ZY plane, A is I. So phi YZ. Now I into I gives me 1, J into I. Vector notations are there. I dot I, J dot J, and K dot K gives me 1. Other than this, I dot J, J dot K, K dot J gives me 0. Okay, so this is everything going on here. So this is your negative sign that implies that the direction vertically downward. This. Is this clear? I mean, why for only YZ plane and ZX plane we have magnetic flux? Is this clear everyone? Okay, because the area vector for XY plane is in the K direction and I don't have my magnetic field in the K direction. Clear beta everyone? Good. Do this. In a magnetic field is strength of this much, a coil with a cross section of this much and 50 turns is positioned with axis this much, flux. That is very easy. Everything is given. And obviously flux is going to be multiplied with the N, which is number of turns. Clear? Do this. Everything is given and tell me how much flux you get. Then we're going to discuss Faraday's law of electromagnetic induction, and that is very simple, d phi by dt, nothing more than that. And then you are free for today. Applications and few questions, nothing more than that. Do this quickly. Okay, as a hint or something, not hint even, solution, everything is given, just give me the answer. Okay, you guys also write in this way, given. What is given? Tesla, and then A, 2 into 10 to the power minus 2 meter square, and then N, 50, and then theta, 30 degree. What more you want? Nothing. Everything in your hand. And there is a formula of flux phi. If you don't know, at least now you're able to do that. NBA cos theta. Put it to this formula. Number 1. Tell me the answer directly now. Then I solved it. Do this. Because the same thing is written on the next page. But just do a calculation. So I want to see how much time you're going to take. It is 9:45 root 3. But how it is going to be root 3? Cos 30 degrees root 3 by 2. And what about that 50? Root 3 have some value, na? Then again. Then what about 100? Oh, nice. 100 is going to be stuck in this. The others get cancelled. Now it is correct. Okay, let's check. 1.732. This, everything given. This. So exact answer is 1.732. Okay. Is this clear, everyone? Everything is given. Clear na? Shushita? Good. Yes, sir. Yes, sir. Okay. Faraday's law of EMI. I already discussed. I give you a hint, a brief. Let's discuss in a proper manner. So what it is in general, Faraday's has proved that two laws that are basis for, that are the basis of the modern electromagnetism. That is Faraday's first law of electromagnetic induction and Faraday's second law of electromagnetic induction. Whatever Faraday's observed in his experiments, like when you move a magnetic field or either you move a coil. So there is a generation of electric current, which is going to be the alternating current, and there is a generation of deflection. So that deflection is going to be electromagnetic force or EMF. That EMF we are going to discuss in a formula wise. So Faraday's first law of electromagnetic induction states that according to this, when the magnetic flux linked with closed circuit, why it is closed need to be? Because if it is not closed, so the current is going to be flow, but it is not going to pass, or it is not going to make a complete circuit. So closed to make a complete circuit. Closed circuit stands for CKT, to make a complete circuit. To make a complete circuit to flow the current. To flow the current. Or this current basically is known as induced current, right, in a proper word. Induced current. Okay. So where we were? Yeah. Circuit changes and EMF is induced in it, which lasts only as long as the change in flux taking place. Focus on this word, as last only as the change in flux taking place. What is the meaning of the change in flux? Until unless there is a relative motion, so the flux is going to be changed, right? It is going to be passes through. The moment there is a relative motion is going to stop, the flux change is going to stop. Why? So what is the meaning of flux change or rate of change of flux? See, rate of change of displacement is velocity. So in a simple way, rate of change of flux is nothing but d phi by dt. Rate of change of flux is nothing but d phi b, or simply d phi, because here we talk about magnetic field, so we don't need to write b again and again. So that is rate of change of flux. As we know, rate of change of velocity, rate of change of displacement or a distance, or rate of change of flow of current is I basically. You can say not current, rate of change of flow, rate of change of charge, or you can say current, or sometimes gives you magnetic field d phi by di by dt. In the same sense, d phi by dt is rate of change of flux. So until unless there is a relative motion, this rate of change of flux is going to be there. Till now you have this induced current or EMF. Okay. So Faraday's law of electromagnetic induction states that magnetic fields can be changed either moving a bar magnet towards or away from the coil, moving the coil into the magnetic field or outside the magnetic field, rotating the coil relative to the magnetic field. This is the principle of AC generator. Important. We're going to discuss, don't worry. Okay. Changing the area of a coil placed in a magnetic field. Why changing the area is going to be also gives you flux change? Because flux is related to two things. For in general, three. Theta you going to change by the rotation. What we are doing by the rotating, we just changing the theta. By changing area, we changing area in simple. So flux is going to be changed. As we know, our flux is related with these three quantities. So B A cos theta. Okay. So either you change theta with this rotation, either you change area simply by changing area, either you change magnetic field by the movement of magnet. Clear? Obviously, if there is a magnet in this, I mean this is my magnet. If I make a magnet in this far away, so the field is not going to affect. If I move closer to this, my finger or a iron nail, so then effect is going to be generated. So that is how I can change. Sorry, that is how I can change the magnetic flux area simply by changing the area of a loop, area of a magnet sometimes, or theta is just rotation. Clear, everyone? So according to second law of electromagnetic induction, the magnitude of induced EMF, that is important one, beta. The magnitude of induced EMF is equal to the rate of change of magnetic flux linked with a coil, and that is your relation. E equals to d phi by dt, and for n number of turns, d phi by dt, this. Okay, this is your second equation for n number of turns. For n number of turns in a coil. For n number of turns for a coil or of a coil, you can write anything. Okay, so E equals to minus phi 2 minus phi 1 by E. Let me check Faraday's second law, which is Lange law. Wait. No. Lange law is going to be teach in the next class. Okay. So, where we were? Here, done. Is this clear, everyone? This negative sign just for the energy conservation. Nothing more than that. Now, energy conservation, where from it arise? Everywhere. It is going to follow. So, as you know, energy can neither be created nor be destroyed. So how this negative sign fulfill this condition? Suppose I throw a ball on the ground. So what ground provide me? Friction. Clear? How much how much energy I apply on the ball, in the same amount, slowly the frictional force is going in the backward direction, and due to this, ball is going to stop. Clear? So in a same sense, this negative sign states that whenever you do the motion, obviously in doing motion you need to do some work, and that work is stored as a energy, or that is going to be stored in the form of magnetic flux energy or something energy, or this induced EMF energy. So this negative, this coil generate a current in the opposite sense to oppose this, and that is basically the Lange law, which we are going to discuss in the next. Is this clear? To fulfill the simple thing, you understand? I will do this and then we discuss, because we are running out of time also. So where E is electromotive force, N is number of turns of the coil, phi is flux change, not change. D phi by dt is flux change basically. This is your flux change. Phi is flux only. Okay. Now we take a magnet approaching a coil. Consider instance at times t1 and t2. So suppose at time t1 flux linked with the coil n phi 1, at time t2 n phi 2 simply. So change in flux n phi 2 minus n phi 2 minus phi 1. So rate of change of flux is this. Good. Or you can say d phi by dt also. This is your rate of change of flux. So taking the derivative of the above equation and d phi by dt, Faraday's law of electromagnetic induction says that the induced EMF in a coil is equal to the rate of change of flux associated with the coil. Thus E equals to minus n d phi by dt. This negative sign is added as it helps to accommodate the Lenz law. And what is the Lenz law basically? See what happening here. Suppose this according to, you can see this, take this as a coil. Okay. So if in this particular coil I try to move this particular magnet towards this. So in this particular coil red end, kind of a bracelet. In this particular coil, my current is going to be generated in the opposite direction. So it tries to stop this, and that is energy conservation. Simple, nothing more than that. In a same sense, you can understand for the ball example. What is the ball example? If you throw a ball on a ground, right? If you throw this ball or if you apply a force on this ball in this way, so this ball is trying to move in this way, but the ground is trying to stop. So the frictional force due to the ground is in this way. This is your frictional force. Static going to be or kinematic friction, because it is in the motion, so it is going to be kinematic friction. And the general force or the force whatever you apply, that is in this direction, force applied. And due to this, this ball is going to be slow down, or you can say at the stop after some time here. And this is energy conservation law. Means whatever energy you apply on this ball, the reverse energy by the ground applied on that ball, and there is net energy is going to be zero. Is this clear? In a same sense, this negative sign is added as it helps to accommodate the Lenz law. And Lenz law states that there is a induced current, or the current generation is going to be in the negative direction. Let me check it is not, or it is given or not. No. Okay, so in the next class I'm going to teach you in a proper manner. Is this clear, everyone? Or we can discuss here as well. Nothing more than Lenz law. What is this Lenz law? Okay, it states that, let me write it down. It states that the induced EMF, it says that the induced EMF or current in a loop is in the negative direction, is in the opposite direction, is in the opposite direction, is in the opposite direction to the flow of magnetic flux. Flow of magnetic flux. Magnetic flux or is this clear now? So this negative sign states that, and that is known as Lenz law. Is this clear, everyone, now? What is this negative sign stands for and what is Lenz law? So sometimes they ask Lenz law directly, and sometimes the reason for this negative sign. So this negative sign because of Lenz law. And what is Lenz law? Lenz law states that induced EMF or a current in a loop is in the opposite direction to the flow of magnetic flux. So why opposite? Sometimes more concept wise. Why? To fulfill the energy conservation law. If someone or if any particular paper you find why in opposite direction, why in opposite direction, opposite direction. So the answer of this particular why is to follow the, to fulfill basic law, which is energy conservation law. To fulfill energy conservation law. Okay, is this clear now? Good. So change in electromagnetic force, this much. Induced EMF can easily be increased by increasing the number of turns. Okay, remember this formula. E equals to minus N. Again, I am saying a wrong thing. Not remember, understand this formula. d5 by dt. Okay, so this is your main thing. So this is E, it stands for electromagnetic force. This is the symbol, which is you can say also have a unit of volt. So we can say that induce voltage also sometimes, because in the previous page I correlate with this a volt into second now. So this is going to be a voltage per unit time. So induced EMF can easily be increased by increasing the number of turns with this. If the magnetic field strength increase, induced EMF also increase. Same thing. Clear? And what increases if you increase the magnetic field strength? Phi B, or you can say phi here instead of B. B dot A. And remember, again I am saying wrong thing. Understand this phi is a flux, which is a what particular type of quantity? Scalar quantity, because it is a dot product of two vectors. Clear, everyone? Clear, beta? It is clear, na? Just type yes or no, anything. You are here, na? Or you sleep? I mean, I bore you that much. Good. Applications of Faraday's law, very important. We're going to discuss in the next slides, or not slides, next classes. Faraday's laws is used in electrical equipment like transformer and electric motors. Okay, whenever we need to change the whenever we want to convert the energy from electrical to mechanical, from mechanical to electrical, we use this particular concept. Simple. How your fan is going to work? Transformer. Transformer is what? Not transformer, that particular movie. Your car is going to transform. Your energy is going to transform. Electric energy is going to be transformed in the form of mechanical energy. Have you ever seen in between the middle part of a fan, what is there? Anyone? There is a toroid kind of shape. Okay, what is that? In general, there is this, okay, and this, and that is having so many copper wire. What is this in general basically doing? So beta, it is nothing but whenever you give electrical energy, so there is a coil, okay, and this coil is generates a magnetic field, and this magnetic field rotated, and in this, this is the middle part. In this we have these three slides now. Okay, I'll go in a proper manner. Wait. This is your one blade. This is your another blade. So this is your third blade. Wow, I draw sometimes some good things. And this is your fan. I'm going to laugh on my drawing. Is this clear, everyone? So this is how your fan just do the work. And in a reverse, like electric motor, what is the meaning of electric motor? Ball bearing, exactly. This is not ball bearing, beta. Ball bearing something else. That is used in wheels, not in fans. That is not turbine. It is this transformer. This is basically transformer. This. For fan I'm telling, not ball bearing. Ball bearing is also used in between this, but the main concept is this one particular thing, na? Like circular kind thing rotated and having n numbers of so many numbers of copper wires in this way. So this is transformer in general. Induction cooker works on the principle of mutual induction, which is derived from the Faraday's law. We are going to discuss. Faraday's law is also helpful in designing musical instruments like the electric guitar, electric violin, and others. So these are the basic things. Now do this question. We have still 25 minutes. A short circuit coil. Okay, let me check. A short circuit coil is placed in a time varying magnetic field. Good one. Electric power is dissipated due to the electric current induced in the coil. Okay. If the number of turns were quadruple and the wire radius half, okay, and the radius of the wire is half, the electric power dissipated would be. Okay, nice one. Find this. Flux is related with area. So area is related with what? What it is? Area is related with what, beta? Radius. Yeah. So if you reduce radius, how much it is going to be? And I just give you one hint. Flux is E, and your power is E square by R. So here we want to find electric power, na? So simple hint. Power E square by R. This E here is induced EMF. Now you find it and tell me. Is this clear? So find induced EMF, do the square and tell me how much it is going to be. Half, same, double, quadruple. Tell me the answer. Tell me quickly. Okay, there is 9-7 and I want to see how much you are understanding this concept, because obviously that is JEE level question, means at least. So 2 minutes I give it to you guys. Enough, 2 minutes. Because I give you the hint already. And turn on the cameras, everyone. Yeah. Solve this one. C is not there. Same, sir. A. Half. Again. Beta, why you put question mark in front of your answer? Parikshit, tell me. Either be confident enough, either don't tell me the answer. Next time. Okay, Vishwanath, half, one. Please tell me C or D also. I want to get every particular answer and then I'll tell you. Because this is kind of KBC, na? Then I shout like 7 crore. Very wrong answer. But very suppose if I am trying, I mean, if I do this, the moment you do wrong and then in some you can say it's not aggression, in some angry expression or sarcasm altogether, 7 crore, and you don't win anything. Okay, 1 minute I give you extra. I want to see more answers. Only 2 are given till now. Are you solving beta side? Okay, it's already 10. I mean 9, 10, not 10. So power is this. Induced EMF is going to be remain same. Okay. Uh, hmm. Where R, my radius is rho, not radius. This resistance is rho L by A. So rho is constant for any particular material. L and A change the resistance. How phi is going to be same? Okay, phi here is B is same. B same. Number of turns. Okay, going to be 4 times. Magnetic field is same, na? Yeah. So here B remains same. So leave this. N is become N prime become 4N, or area become A by 4. Why so? Because R is radius now. Okay, radius R prime is R by 2. And we know area is pi R square for any particular coil simple. So A prime is pi R square by 4, which is A by 4. So due to this, okay, phi prime is B remains same, N prime, which is N into 4, A prime is A by 4, which is A by 4, 4 cancel, and then this same. So rate of change of same also. So R resistance, R radius, L length of wire. So this power is inverse. E square means N square, R square means radius square, L square. L remains same, N R square. So in this way you can get this. The correct answer is B. Is this clear? So when this particular type of questions you are facing, so try to find the AND dependence. AND dependency is here N or R. R is what? R is beta. Here small r is radius, capital R is resistance. This one is your resistance, and this one is your radius. Clear? Is this clear, everyone? I hope and believe is this clear. Should I move ahead or repeat this thing? I don't need to. Okay, do this. A solenoid has this much turn over a length of this. Around its central section of coil, this much turn. Area this much. Initial current of a 2 ampere in the solenoid, reversed in this. EMF you need to find. That's the main thing. Everything is given. Magnetic field you need to find also here for a solenoid, which is mu Ni, or mu capital Ni divided by L. So find magnetic flux. Sorry, find magnetic field first, then magnetic flux, which is N prime Ba, then induced EMF, which is d phi by dt, which is d by dt of N prime Ba. Here B is going to be changes, T is there, everything is given. So tell me the answer. This is your last question for the day in this particular session. You can see in the PDF of this, and then we are going to do the this thing. This thing is CA, class assessment. Do it quickly. I'm not going to give you every time a hint. It's your job to do this. Hint I simply elaborated. Like first of all, find the magnetic field due to the solenoid, then magnetic flux due to this change in area. Okay, area is same, and if initial current is 2 ampere, it is going to be reversed. The direction of current is going to be reversed. So due to this, phi is going to be changed. Area is there, turns is there, solenoid is there. You see, this is N, number of turns for coil. This is number of turns for solenoid. Don't confuse in between these two. Is this clear? 2000 is the number of turns for a coil, and 100 is the number of turns for a number of coils, basically. Okay, what is this here happening there? See, you get a magnetic field. There is one solenoid of yours. Okay. In this particular solenoid, we have 2000. Assume this. V I. So these are 2000, and then length is given already. Okay, and then we have this one also. So this is 100 number of turns in a coil. This is for solenoid. Do this quickly. Someone is messaging me. Don't do this. Okay. Or should I tell you because you take much time? Okay, let's see. The answer is B, and how so? Because you are not responding anyone. So magnetic field at the center of a solenoid is this B, which is mu naught Ni, capital N upon length, 4, 3.14 into 10 to the power 7, 4 pi into 10 to the power 7, 2000 by this, and 2. So that much is your magnetic field. Magnetic field is perpendicular to the plane of coil, so NBA directly. When it is perpendicular to the plane of coil, theta is 0 degree. And when theta is 0 degree, N prime BA. N prime is 100 here. Induced EMF is minus d phi by dt minus d by dt of NBA minus NA minus B minus B. What is the sense of minus B minus B? Because it is going to convert its direction. So 2N prime BA. Okay. This is phi 2. Okay. Phi 2 is minus NBA. Phi 1 is NBA. Simply. Or N prime. So we take N prime or A common. Minus B comes from here. So that is the sense. Is this clear, everyone? Is this clear, beta? Dhaveshwaram, Sai, Susita, Parikshit, Kyle, Netra, obviously she is there now maybe. And Vishwanath. Clear? Okay. So we discussed so many important things. Now there is a class assessment. Do it. Okay. So as a summary, experiments of Faradays and Henry, observations, magnetic flux, and Faraday's law of induction. We all done in this single, that is important thing, and that is the beginning of EMI and the basis of AC and some principal concepts. Okay.